So first of all, we're going to talk about the pH. And what's interesting about pH, the P stands for proportion and H stands for hydrogen or the positive ion of hydrogen. So this is from the fact that we live in nature. Water is one of the it's an abundant substance on the planet. And when you have liquid water, what's interesting here is that the way it is organized, water has a polarity. So let's see what it means. So on this side, I did some Lewis dot diagrams of two water molecules. So what's interesting here, you could see that here we have the oxygen with 8 electrons in its valence shells, and here we have hydrogen here and hydrogen there with 2 electrons on the outer shell. So things are beautiful this way. Now you have to keep in mind that the electrons are going at the speed of light. So that means that ever so often the electron from this hydrogen gets closer to the oxygen right here. That means that the overall grouping here of hydrogen and oxygen becomes overall negative. And here you have a hydrogen that is by itself, and it is a positive ion of hydrogen. But because the electrons are going at the speed of light, and here we have a hydrogen that has a positive charge, this will attract a hydrogen ion from somewhere else or the same grouping here. So what will happen? This one says here, I need electrons, so it will pull electrons so that it has a full outer shell. That means that the hydrogen here will be given its electrons here. So overall, you have here, so if you take the other example here, this becomes negative, and here you're left with a positive hydrogen ion. So here it goes back and forth, keeping in mind that the hydrogen here could decide to take electrons from this grouping here of OH. OH here, we call it a hydroxide polyatomic ion. So here, this one could go here, and this one could go here. What happens here, you have exchanges of hydrogen ions. Okay, so that's the first thing to consider. Now, if you notice, if this goes at the speed of light, wherever we have the oxygen tends to be more negative, and the other ends here ends up being positive. And that's what makes a water molecule having a polarity. So here, this is more negative, this is more positive, and if it goes like this, positive, negative. So overall, you have one portion that tends to be more negative, and you have the other two ends that tend to be more positive. And that's beautiful because water is an amazing solvent, and it will dissolve different substances due to this charge. So that's the first thing. Second, how does it work? We have a water molecule, and then we end up with ions. So let's take a look at this chemical formula. If you have a water molecule, momentarily you end up with a positive hydrogen ion, and here you have a negative polyatomic ion. Now, sometimes people, instead of H plus, they have H3O plus like this. It all depends where you are studying. So that H plus here would be going with H2O, giving 3 hydrogen and 1 oxygen. But I like this way, so I'm going to continue this way. So we know that momentarily, one molecule of water creates 1 hydrogen ion, and here 1 negative hydroxide polyatomic ion. But as soon as we have these, because of the opposite charges, they go back and recreate the water molecule. So here we have an equilibrium or chemical equilibrium where we have water molecules going to ions and ions going back to the water molecule. Now, what's interesting here is that if there's an equilibrium and we have distilled water, what's interesting is that we have here a pH of 7. pH of 7 is the neutral solution. Now, what does that mean, pH of 7? Is that there is 1 hydrogen positive ion per 10 to the positive 7 water molecules. So let's see if I can simplify it and make it a whole number. 1 over 10 million. So what happened here is that if you have pure water, out of 10 million water molecule, one molecule will be transferred to this, and then as soon as it goes here, it goes back to water, but somewhere there's another molecule, water molecule, that will be going this way. Having an equilibrium, that means that there's one hydrogen ion per 10 million water molecule. So we're talking here the proportion of positive hydrogen ion. So this is what pH 7 is. It's a proportion. So let's see what happens if you have a pH that goes into the acidic portion of the pH scale. So here we have 7. Let's go to pH 6, 4. I'm going to also do pH of 2 and 1. Give me a second. We'll check. I'll be back. So what happens when you have acids? When you have acids, you have a pH that is lower than 7. For example, pH of 6, pH of 4, pH of 2, and pH of 1. So how do we know what it means? It means that there is a proportion of hydrogen here, hydrogen ion, much more present. So if you have a pH of 6, it is a ratio of 1 hydrogen ion over 10 to the power of 6 molecule of water. That means 1 over 1 million. If you have a pH of 4, it is 1 over 10 to the power of 4, which is 1 over 10,000. So there's 1 positive hydrogen ion per 10,000 water molecules. So as you can see here, there's more and more hydrogen ion here. If you go to a pH of 1, which is very, very acidic, so sometimes we think of hydrochloric acid, for example. So that means that every molecule that is of HCl dissolved in water will bring more hydrogen. If you have sulfuric acid with H2SO4 dissolved in water, you have an input of positive hydrogen ion. So here what happens, you end up with 1 positive hydrogen ion out of 10 molecule or 10 particles. So you can see here the concentration is quite higher. Now what's interesting here is the more and more hydrogen ion you have here, the more there is a possibility of interacting with its environment. So for example, if you have hydrochloric acid or sulfuric acid on your skin, what will happen is that the hydrogen ion, which are positive, will be looking for electrons. We'll find in the organic tissues molecules that can be broken up to give to that H plus electrons and other components to create new molecules. Consequence, we have the skin that is disintegrating. If we look at let's see if we can look at the pH scale. So we have this one here. So let's see, pH scale is right there. Perfect. So if you look at the pH scale, so we have here at 7, we have distilled water, same number of H plus and OH minus. But as further down you go in acidity, all the way to hydrochloric acid, you have here more and more reactive. Hydrochloric acid, it is very damaging. Now, if you were to look at food, for example, and you were to take, for example, oranges and grapefruit, you'd have an acidity that would be around here. So this is, I don't have the exact number, but it gives you an idea. But if you take limes and lemons, they're much more acidic. There's more citric acid, and you can feel on your tongue when you taste it. The reaction is much stronger. Very nice. Now you have to keep in mind that if you have cola or even mineral water, you have acidic, how do we say that? Solution. Let me show you why that is. So here's an example of why pop or mineral water would be more acidic as a solution. So when you have a cola, any cola you like, you have ingredients, sugar, it's dissolved in the water, and then you add carbon dioxide to create the bubbles. We like the bubbles. What do we get here? We get a sugar drink that we enjoy. But what's interesting is that even though we drink it, inside that fluid, we have water and carbon dioxide. And when you put them together, let's see, you have 2 hydrogen, you have 1 carbon, and then you have 1, 2, 3 oxygen. You end up here with what we called carbonic acid, which is a weak acid. But one of the consequences of that, it can disrupt your digestive system, but also your teeth. You can have what we call acid wear for someone that is drinking too much pop or carbonated beverages, and it's not good for your teeth. The acidity of the liquid is reacting with the enamel and the structure of your teeth and weakening your teeth. So that's an example of reaction in your body. So let's see, we've talked about acids, we've talked about the neutral water. Let's see if we can look at pH that has a value bigger than 7. So let's have a look. So what happens if you have a pH that is higher than 7? So let's see. For a pH of 8, that means that the proportion of the hydrogen plus ion is 1 out of 10 to the power of 8, or 1 over 100 million particles. If you go to a pH of 12, which is the proportion of hydrogen is 1 over 10 to the power of 12, then here we end up with 1. So this is 1 million, billion, and 1 trillion. So out of 1 trillion hydrogen positive hydrogen ion. There you go. If you have a pH of 14, then it's even smaller. And then we end up with billion, trillion, and quadrillion. So you can quadrillion with an N. So you can see here the concentration of hydrogen is decreasing. And how is that possible? So let's see. So when you have a pH that is like 8, pH of 12, all the way to pH, for example, of 14, and an example of that would be you dissolve in water sodium hydroxide. So in the solution, we're adding sodium, but we're also adding OH minus like this. So here you have a solution where you are increasing the quantity of OH minus like this. And because there's an increase of the negative polyatomic ion, these will interact with the positive hydrogen ion, and therefore decreasing how many of those there are in the solution. So that's an example on how we can have a pH that is 10, 12, or 14. It's not that there's no hydrogen, positive hydrogen ion, is that they have been decreased in proportion due to other components in a solution that are taking away those hydrogen ions. So that's how we have a pH that is changing. So if we are looking at the pH scale, let's look at this one, perfect. So here we have a pH of 7, which is neutral. And then we have here in the ocean, the idea here is that over the millions of years, we've had rock erosion that are bringing in the ocean components that are taking away the hydrogen, the positive hydrogen ion. Now, if you are in pH between 8 and 14, we have what we call alkaline environment or alkaline solution. So two that we often can think of are soap. So soap that we are using when we wash our hands, or laundry detergent. So what we have here, and I'm going to show you an example. Let's say that you have a molecule. Let's say that you are going outside and you have some dirt, and then you put in the wash, or it's on your hand. You have a long molecule of a substance, and when we put it in contact of an alkaline solution, what happens is that this long chain, this long molecule, breaks down in smaller pieces, and therefore it's more easy to clean, and therefore we have clean clothes, a clean body. For the same reason, some of you may have noticed that sometimes you go to a restaurant or you go and eat at a friend, you eat spaghetti, and then if you wear something white, you have, let's see if I can make it bigger, some spaghetti sauce, for example, comes here. Some companies are creating that like little, it looks like a pen, and there's some detergent in it. And then when you tap it on your like spaghetti sauce that is red, you notice that we have all the stain is going away. So here's an example. You have a stain, a piece of like a long molecules of spaghetti sauce in contact of the detergent. The long molecules that are red will be breaking down like this into something that are smaller. So on your shirt, you end up with, you still have, it's still dirty, but the molecules are all small and have no colors, and therefore that's why your clothes look clean. You still have to clean your clothes, but that's how detergents are working. And something that is interesting, you felt it when you wash your hands or you have detergent. One of the properties of bases is that in your fingers, it feels it's a bit gooey and it's very slippery with respect to the texture. If you go all the way to a pH that is much higher, for example, 12, 13, and 14, then you end up here with the sodium hydroxide that I mentioned right here. Let's see if I can make it bigger for you so you can see. So you have here sodium hydroxide that is bringing to the solution a lot of OH minus. To the opposite end, we have hydrochloric acid, when dissolved in water, are bringing high concentration of positive hydrogen ions. Now, what happens if you put the hydrochloric acid and sodium hydroxide together? And that's the next chemical equation we're going to look at today, together today. So let's see. So here, if you're in a situation where you have a strong acid, like hydrochloric acid, and you put it with a strong base, which is for here, sodium hydroxide, what happens is that when you put them together, you will have, first of all, what we call a double displacement. So here, what will happen, you have the hydrogen that is more reactive. So the hydrogen will take the place of the sodium with the hydroxide. So hydrogen and OH to create liquid water. What do we have left? We have here chlorine and sodium that will create sodium chloride, which is here a salt. Interestingly enough, even though we had a very strong acid and we had a very strong base, that double displacement created a solution that has a pH of 7, no longer acidic or basic, and a salt. This type of reaction we called a neutralization reaction. So here we have a double displacement, and that is resulting in a neutralization. So that's quite interesting. So chemically speaking, it is amazing. So this is basically the topic I had to add for you today. So if you have any clarification question, you can please put them in the comments below. Otherwise, I'm going to see you in another chemistry video, and I'll see you there in a moment.